Hey Global Impact students, this is Mr. Ellinger. This lesson is on patterns in nonlinear functions. Our last lesson was on patterns in linear functions, so we're going to take a look at nonlinear functions here. Our learning target is to identify and represent patterns that describe nonlinear functions. So the essential understanding, just like with linear functions, nonlinear functions can be represented using words, tables, equations, sets of ordered pairs, and graphs. A nonlinear function is a function whose graph is not a line or part of a line. In the real world, some situations are modeled using linear functions, while many other situations must be modeled using nonlinear functions. Linear functions are much more basic and will be examined first, but later in this class, and much more in higher level math classes, we will look at nonlinear functions. Right now we need to understand that any function that does not form a straight line on a graph is what we call nonlinear. So just like linear functions, nonlinear functions can be represented using words, tables, equations, sets of ordered pairs, and graphs. So just to kind of review a little bit, a linear function is a function whose graph is a non-vertical line or part of a non-vertical line. So here we have some examples. Here we have a line drawn on our page. Here we have a set of points that form a line, linear pattern. And then here's another line, just a horizontal line. And that's going to be a special function that we'll get into later. A nonlinear function here is just three examples of nonlinear functions. A nonlinear function is a function whose graph is not a line or part of a line. So here we have this U-shaped curve. That's called a quadratic function, which we'll look at later. Here we have this strange looking curve. It's kind of like a line that's just bent or distorted. That's actually the graph of what's called a cubic function. And then here we have just a set of points. Remember, this is called discrete data. There's no line connecting them, it's just a set of dots. But they make this V-shaped pattern. And this V-shaped pattern is actually illustrative of what's called an absolute value function. So we'll get into some of these functions, like it said, later in this class and then later in other math classes. All right, so let's get right into an example here. The area A in square inches of a pizza is a function of its radius r in inches. Okay, so we're assuming this is a circle. The cost, C, in dollars of the sauce for a pizza is a function of the weight in ounces of sauce used. Graph these functions shown by the tables below. Is each function linear or nonlinear? So here's the pizza area data, and here you can see some different radius values of the pizza. So when the radius is 2 inches, the area of the pizza is 12.57 inches, and those values are being generated by the area of a circle formula, which is A equals pi r squared. So that's where these values are coming from. Okay, so you can see we've got radius values of 2, 4, 6, 8, and 10, and we have different area values. Now, what you'll notice is these area values, going from the first one to the second, we've got an increase of about 38. And then from the second to the third, we've got an increase of about 63, an increase of roughly 90, okay, and then an increase of roughly 113. So definitely the increase here is not consistent, okay, or constant from one area value to the next. Now the radius values they're going up by 2 every time, but the area values are not going up by the same amount. And if we look at the sauce cost data, again, our weights, 2, 4, 6, 8, 10, that's constant change, increasing by 2 every time. Here's our cost. Our costs go from 80 to 160 to 240 to 320 to $4. So every time there's an increase of what? 80 cents. So that's consistent every time, right? So there's definitely a difference here. The relationships shown in the tables are functions. We need to be able to classify the functions as linear or nonlinear. So one of these is linear, one of them is not. And we need to use tables to make graphs. So if you remember our last lesson, this sauce cost, this is an example of a linear function. Okay. As our input values increase by the same amount, our cost values are also increasing by the same amount. So that's where we get the linear function. Over here with our pizza area, this is a nonlinear function. because as the radius values increase by a constant amount, the area values do not increase at a constant amount or decrease. It could be decreased too. So if we plot our values, graph A is a function of R. Here would be 2, 12.57. Here's 4, 50.27. Here's 6, 113.10. And so on. Here's 8, 201.06. And here's 10, 314.16. Now before the line is drawn here, it should be fairly clear that if I were to try to draw a straight line through 2 of these points, it's only going to go through 2 of those points. I can't hit any other points with a straight line. So there is this curved nature to the graph, okay? Curved nature, again, we can see how like between these 2 points, if I just connect these 2, and then I just connect these 2, and then I just connect these 2, the change is getting greater in terms of the area. The graph is a curve, not a line, so the function is nonlinear. Sauce cost graph. If I plot my ordered pairs here, I've got 2 and then 80 cents, $4, $1.60, 6, $2.40, 8, $3.20, 10, $4. I can connect all those with a straight line, so this is an example of a linear function. All right, so here we have a table shows fraction A of the original area of a piece of paper that remains after the paper has been cut in half n times. Graph the function represented by the table. Is the function linear or nonlinear? Well, let's draw a graph here. And I will put on my horizontal axis here my dependent variable, on the horizontal axis here, my independent variable is the number of cuts, n, and then my vertical axis is going to be area remaining, and they call that capital A. Okay, so our variables are n and a in this problem. Now we're not writing an equation, we're just graphing this, so we don't have to know the variables, but if we were going to write an equation from this, we would need to know the variables. So the way we're going to scale this is we have cuts of, in increments of 1. So here we have 1, 2, 3, 4. Area remaining, what's happening to the area? Well, the area is actually decreasing, and it's decreasing. The largest of these values, area values, is a half. So we could go up here to a half an inch, and then a fourth of an inch. Well, think about a fourth of an inch. A fourth of an inch is half of a half. So if 0 is here and 1/2 is here, then halfway between here and here would be a fourth. So I'll just kind of ballpark this. Here is 1/4, and then half of that would be 1/8, and then half of that from 0 to 1/8 would be 1/16. All right, so there's my values, and I'll just go ahead and plot these points. 1, 1/2, so I go to 1, and then I go up to 1/2, put a dot here. When n is 2, the area remaining is 1/4, so I will put a dot here. When n is 3, the area remaining is 1/8, so I'm going to put a dot here. And when n is 4, the area is 1/16, so I will put a dot here. And if you take a look at those values and the pattern that's, developing here, this is a nonlinear pattern, okay? Now, I could go ahead and draw a curve through this. The curve would look something like this. It would follow this pattern here of my cursor. I'm not going to draw this because I believe that this data is probably discrete data. We can't cut a paper 1.75 times. We can cut it once, we can cut it twice, we can cut it 3 times, we can cut it 4 times. But you should be able to see the nonlinear nature of the data, okay? So part B, this question here is actually a calculus concept, okay? And calculus is is a class that you will probably get to. There's quite a bit of space that we have to fill in between Algebra 1 and calculus, but we can still talk about calculus concepts. The question is, will the area A ever reach 0. So that means like the graph, if the graph were to ever come all the way down here and hit the x-axis somewhere, that would mean that the area was 0. So let's think about this for a second. We're cutting paper in half. Can you ever get to the point where there is no area left, meaning there is no paper left? Okay, so you cut it so many times that there's no paper left. And you might say, well, I don't think so, but there's going to come a point in time when I really can't cut it in half anymore because it's so small. And that's true. You know, the paper is going to become so small that with our scissors and things, we can't actually cut the paper. But if you think about what this is asking you in theory, really you can continue to cut things in half, cut something in half, half. You're never going to get to the point where a half is 0. Because if you have some paper, you know, it might be microscopic in size, but you could still, in theory, cut it in half. Now, in practicality, you can't cut it in half because we don't have scissors that are going to be small enough to continue to do it. But in theory, we could continue cutting in half. So what this means is this data, if we were to continue this out for like 10 cuts, 15 cuts, whatever, the graph of this, these points are going to get very, very close to the y-axis. Okay, so let me take this dot off. So these values are going to get very, very close, okay, to the y-axis, but they'll never actually get to the y-axis. We can never, ever get to a point where we don't have any area or 0 area, and that's a calculus concept. It's called a limit, okay? So the limit here would be 0. The limit on the area would be 0. The limit on the area would be 0, but we can never actually get to 0, okay? So there you go. You learned a bit of calculus today. All right, so here's another table, some data. The table shows the number of new branches in each figure of the pattern below. What is a pattern you can use to complete the table? Represent the relationship using words, an equation, and a graph. What you're seeing here in this picture, these are called fractals. Maybe you've seen fractals before. But what's going on here is, in the figure, the number of figures, x, is 1, and the number of new branches would be our y value. So when we have one of these, we have 3 branches drawn. And then off those 3 branches, we can draw 3 more branches. And then off those branches, we can draw 3 more branches. So what's happening here is, as x increases by 1, y is increasing, but how so? Well, this one, you got to kind of look at the data a little bit. You know, when we go from 1, when x is 1, we get y is 3. So it might look like, well, maybe it's 3 times x. Well, then when we get to the second one here, if x is 2 and y is 9, we can't multiply x by 3 to get 9. Okay, so it's not 3x. So let's take a look here. As when x is 3, y is 27. So the numbers are increasing very rapidly. So what we have to do, there has to be some exponents involved here. So we might say, oh, maybe it's x squared or something like that. Well, 1 squared is not 3, so that throws that out right away. But we have these other types of functions that are called exponential functions. See, when x is 1, y is 3, so that maybe 3 to the x power is what we're looking at here. 3 to the first power is 3. 3 to the second power is 9. See, if x was 2 here, 3 squared is 9. If x is 3, 3 to the third is 27. 3 times 3 times 3. Okay? So 3 to the fourth is 81. Okay? 3 to the fifth is 243. So those are our values that we need to fill the table. So, you know, again, I kind of developed the equation first, but if I just look at the pattern here, I'm multiplying by 3 every time, right? Times 3, times 3, times 3, times 3. So as x increases by 1, y is being multiplied by 3 every time, and that's an exponential situation, okay? So 3 times 3, times 3, times 3, times 3 to get this value out here. So the way that we write this shorthand would be 3 to the fifth. That's the pattern, okay? So in general, it'd be 3 to the x power. So that's the equation. Now the graph of this, if I wanted to sketch a quick graph. Okay, when x is 1, y is 3. So if I scale these by 3s, 3, 6, 9. Okay, and this is going to these are getting large very quickly. So as you can see, my graph is not great, but 81 is going to be way up here. And I'm going to draw over the top of this. 243 is going to be way up here on my graph. Okay, so when x is 1, y is 3. When x is 2, y is 9. When x is 3, we get 27. When x is 4, we get a value of 81. And when x is 5, we get a value of 243 way up here. So you can see it's not linear. Okay, so the general nature of the graph is some curve upward. All right, now I didn't hit the points, but we're just looking at the shape. This is definitely non-linear. Okay, this is actually what's called exponential. Okay, this is an exponential function. This is an exponential relationship. Key is the variable is the exponent itself. So we'll look at exponential functions in a couple units. So there's an introduction to it. Okay, so our last bit of information here in this lesson, a function can be thought of as a rule that you apply to the input in order to get the output. You can describe a nonlinear function with words or with an equation, just as you did with linear functions. So here we have ordered pairs 1, 2, 2, 4, 3, 8, 4, 16, and 532. Those ordered pairs represent a function. What is a rule that represents this function? Okay, so here we have some ordered pairs, so we can make a table to organize the x and y values, because I think that a table is easier to see the pattern that is there between x values and y values. Okay, so if we write our ordered pairs in a table like this, what we have to do is we have to figure out what rule produces 2 given an x value of 1. Okay, well, there's a couple different options here. So we start off with this first ordered pair and we say, okay, how can we get a 2 from 1? Well, there's different options. We could have y equals 2x, we could have y equals x plus 1, we could have y equals 2 to the x. All of those x values of 1 in these equations produce a y value of 2. So that's kind of like a starting point. And then what's going to happen is, as we look at the rest of the ordered pairs in the data, we're going to kind of eliminate these possibilities to see what in fact is the equation of the rule. So y equals x plus 1 does not work for 2, 4, because if x is 2, we add 1 to it, we get y is 3. Okay, so right away we can throw this one out. Y equals 2 times x works for 2, 4. Okay, because when x is 2, we multiply it by 2, we get y is 4, so that works. But then when we go to our next ordered pair, 3, 8, that doesn't work. If x was 3 here, 2 times 3 is 6, not 8. So we throw this one out. Okay. Now, 2 to the x works for 2, 4. If x was 2, 2 squared is 4. If x is 3, 2 to the third is 8. So it works. Now we just need to kind of go down here and see if does it work for 2 to the fourth. If x was 4, 2 to the fourth, that's 2 times 2 times 2 times 2, that's 16. And then 2 to the fifth, does that work for that? 2 to the fifth is 32. So that is, in fact, the function rule for this data. Okay? So the function can be represented by the rule y equals 2 to the x. So again, when we have to write a rule, and this is not that easy to do, we just start off with our first ordered pair, think of some rules that could apply, and then as we go down the list here with our other ordered pairs, we can eliminate the possibilities, and then once we find a rule that applies to like the first 3, we just see if it applies to the rest of the data in the table, and usually it will. And once we get that, then we establish that as our rule, called our function rule for the data. Okay, so again, discussing nonlinear and linear functions, we need to be able to identify them from a graph, and usually that's pretty straightforward. It's either a line or a curve. But we also need to be able to identify linear and nonlinear from a table. Okay, and again, it's just a matter of looking at our x values and our y values. If both are increasing at the same rate every time, that's called a linear function. If our y values are increasing or decreasing at a different rate from one x value to the next, then we get what's called a nonlinear function. Okay, so that's it for now. Hope you guys have a great day.